in some cases, when we deal with motion, we have to worry about what the motion is relative to. For example, consider these two cases. You are on a train that is traveling 40 miles per hour north. You are walking at 5 miles per hour towards the front of the train. That means you are moving at 5 miles per hour north as well. The question is, what is your speed relative to the ground? So relative to the train, you are moving at 5 miles per hour north. People sitting in the train are going to see you moving at 5 miles per hour towards the north. However, because the train is moving at 40 miles per hour towards the north, your velocity relative to people outside is not going to be just 40 miles per hour or just 5 miles per hour. It's going to be the sum of both, 45 miles per hour, which is the 40 plus the 5, since both are in the same direction. In the same token, if you are walking backwards, walking towards the rear of the train, now the train is moving north, you are moving south. Relative to people inside the train, you are walking at 5 miles per hour towards the south. For people outside, they see the train as moving 40 miles per hour north, but you are moving relative to the train at 5 miles per hour south. So your velocity relative to these folks outside is not going to be the 40 miles per hour, it's not going to be the 45, since the train is moving towards the north while you are moving towards the south. So it's going to be 35 miles per hour. What if you are walking sideways across the car of the train? What is your speed relative to the ground? To try to discuss this, we are going to look back at the previous two cases. Let's go back to the previous two cases. Now, in the first case, the velocity of the train is pointing in this direction. Velocity of the train. So let's call it velocity of the train relative to the ground. So VTG. So we are using two subscripts. The first one is the object that's moving. The second one, it's relative to what? Velocity of the train relative to the ground. Now in your case, you are moving in this direction as well. So that's the velocity of the person relative to the train. Now these two velocities are in the same direction. The overall velocity of the person relative to the ground is going to be the sum of these two. That's the 45 miles per hour. It's going to still be towards the north. Now, excuse me. Now in this case, the train is still moving north at 40 miles per hour. But your velocity is pointing south. Velocity of the person relative to the ground is south. So your overall velocity is going to be the sum of these two vectors again. In the first case, when we did the sum, we just added up the magnitudes, since they are in the same direction. But in this case, the sum has a magnitude actually of 35. Remember the tail-to-tip method. So we have this one, and then at the tip of this one, we have the tail of the second one, and you get the sum from the tail of the first to the tip of the last. That's my 35. So that's the way we came up with the 35 miles per hour using vector notation. Now when we come here, in this case, the train is still moving relative to the ground at 40 miles per hour. But you are moving perpendicular to it, sideways. This is your velocity relative to the train. We are going to apply the same rule. So this is your velocity relative to the ground. Of course, from here you see it's going to be bigger than the 40 miles per hour. We don't have the exact value, but we can calculate it. The magnitude would be the hypotenuse in this triangle here, so we can calculate it using the Pythagorean theorem. So this is my answer.